coil. Okay, and in this coil, as you can see right now, the current is in upward direction. So that's how you have to hold this your with your hand. You have to hold it like this, and if you do that, you can see the direction of the magnetic field is towards this thumb. So direction of magnetic field is towards this direction, right? And we should also know that if there is a magnet, a bar magnet, correct? So in bar magnet there are two poles, say north and south. In this bar magnet, these there are, just like a charge has electric lines of forces, same way magnet has magnetic line of forces. And in the beginning we just understand from where it enters and from where it leaves. So this is how a magnetic line of force you will look like. So it comes out from the north pole of a bar magnet and enters into the south pole, right? And there are these magnetic lines inside the magnet as well. So this is how magnetic lines of forces are. This is important because this actually gives us an idea about where is north pole and where is south pole of a magnet, right? So this is the north pole. From north pole, magnetic lines will appear to come out. Now in this solenoid, if it is like this, the lines appear to come out from this direction, in this direction. So that's why this is the north pole and this one is the opposite pole, is the south pole. This is applicable for even a single coil. Suppose there is a coil like this, right? And suppose in this coil there is some current flowing, and let this be the direction of current. So this is direction of current. Now again apply your right hand rule. So you place your right hand, four fingers, in the direction of current. So it will be in a circular direction and the thumb will actually come towards you, right? So the thumb comes towards you. So let's show that direction as dot. So this is the direction of magnetic field, and its just opposite will be when the current will flow in the opposite direction. So suppose now current flows in this direction, that is clockwise direction. So if it is flowing clockwise direction, now again you place your thumb, your fingers in the direction of current. So now your thumb will be actually going away from you, or will be pointing in direction away from you towards the screen, or you can say from the screen it will go to the back side of the screen. So it will look like this. So this is how the coil and its magnetic field or magnetic field's direction behaves. Now, if you see this properly, the first case and the second case. In the first case, the magnetic line of force is coming towards you. That means what? That means this side of the coil is actually behaving as north pole, right? And in this section, it is actually behaving as south. So that when you are seeing the current in anti-clockwise direction, the magnetic lines of forces are coming towards you. That means that portion of the wire is, or that side of wire is behaving as north. Now assume yourself on the back side of this coil. Suppose you are observing from that side. Now if you apply the same thing, or even if you are not there on that side, if it is appearing, if the magnetic lines of forces are, say, appearing to come towards you when you are in the front of the screen, say it is coming like this, that means obviously it will be entering in this direction. So the person who is on the back side, what he'll see lines going away from him, right? So for him, that is south pole, And but for you, if a person is standing here, for him the same coil is North Pole. So that's how even a magnet behaves. If you are observing, if observer is on this side, what he says, he sees the North Pole of the magnet. And if the observer is on this side, what will he see? He will see the South Pole of the same magnet. The same thing here happens here as well. So we can say that this coil actually behaves as a bar magnet, as a very small bar magnet, right? And when there are multiple coils like this, so the same thing happens here also. It will behave as a bar magnet itself. Now to remember this, the direction of magnetic field and the current, we have a small trick here. So if you see, this was the first case. This is the direction of current, right? And what happened to uh, the about its magnetic pole? Which pole is this towards this? So it is North Pole. So actually you can think of writing N like this, right? Or the opposite, that is writing S like this. And in that case, if I have to draw the circuit and the current direction will be like this. So if this is the current direction, this is actually South Pole. I mean, this end or this portion or this side of the coil will behave as South Pole, right? So now coming back to the same thing in the animation once again. So you can see this if I connect it like this, right? And if I show current direction, let's increase the voltage. So you can see now current is flowing, and current is in direction from top to bottom in the front section. But in the back section of this coil, it is actually moving in bottom to top direction. Same way, if a person is standing, if you are suppose watching this from the side of compass, so it is actually going, the current direction is actually clockwise direction. It is going in this direction. It is a clockwise direction, right? But if a person is on the right hand side, that is opposite to the compass, if a person is here, that person will actually see the current moving in anti-clockwise direction, right? So for that, it will be anti-clockwise direction because it is anti-clockwise direction. So that is that this right hand side will actually behave as South Pole, sorry, North Pole. And that's why you can see this compass is actually the red is actually pointing towards the right side. That means that is the north direction due to, or that is the North Pole of the this particular magnet, right? So this is, and when we change the direction of the current, we will see that the magnetic field or the current direction has changed, and now the compass has also changed its direction, right? And if you want to see the resultant magnetic field vector, this green line inside the coil is actually our resultant magnetic field, right? So now let's get back to the derivation part. So we have to find out the magnetic field inside this solenoid. Okay, the solenoid has, okay, this solenoid which we have seen uh, has various parts, right? So suppose it is made like this. Okay, so now you will have to see, or you will have to see, or suppose we cut this into half and you are seeing the top view of that. So the top view will look something like this, right? And in these, there are wires coming like this. So these are the wires which are there wound on the, and suppose we have cut this and we are able to see, somehow we are able to see inside this. Okay, now suppose the direction of current in each of these coil is upward, like this. So that is the direction of current. Okay, the section which you see here, these dots, right? There, the wire is, you can assume that wire to be a straight wire coming towards you, that is perpendicular to the plane of this screen or perpendicular to the screen. So if those wires are perpendicular to the screen, that means it is a straight wire. That section of the ground wire is actually, it can be taken as a straight wire. Then you will have to keep your thumb in the direction of the current. And if you do that, your thumb will actually point to the back side of your screen. And in that case, the magnetic field which will be generated will be something like this. The magnetic lines of forces, suppose I draw only for this, it will be like this. And what will be the direction of this magnetic lines of forces? It will be it is going downward. So the magnetic lines of forces will actually look like this, or will be in this direction. This will be the direction of magnetic field. Just like on electric line of forces, right, or lines of electrostatic forces, there the tangent to the curve or the line or the path actually shows the direction of the electric field. Same way here, it will show the direction of the magnetic field. Now, assume, or let us consider its neighbor, which is this point. So at the neighbor, this, here also there will be a magnetic field like this, and even there the direction will be like this, right? So direction is like this. Now see what happens. If you see inside, right, inside the points which are inside, these, the tangent here will be in this direction. So this will be the direction of magnetic field. For the first line also, it will be in the same direction. So what do we see here is these magnetic fields inside, they are all in the same direction. And that is the reason, because they are all in same direction, the resultant magnetic field is actually along the axis. It's not like there is no magnetic field here, there is no magnetic field here, it is there, but along the axis, you can say the direction will be along the axis itself. What about other components of magnetic field? There will be magnetic field here as well as here. So now you see this part, this direction is like this, it is in clockwise direction. So here also it will be like this. Now if I magnify this part, right, if I magnify only this part, this the blue circles, if I magnify, it is actually like this. This is magnetic field due to one wire, and magnetic field due to other wire will also be same. It will be the same. I mean, the direction of that magnetic field will also be same. Just wait for some time. There is power cut here. Yeah. So this is one magnetic field, and similarly there will be other magnetic field. Let us see the magnified view of that. So these are the two. You can say this magnified view is here. Now what do we see here? There is, or the first one that is on the left, it is actually like this. Then here magnetic field is like this, and here in the second one magnetic field is like this. So obviously what will happen to these two, if they are symmetrically or you can say uniformly placed points, then obviously these two magnetic fields at this point will cancel each other. At this point they cancel each other, and just like there is magnetic field here, same way there will be magnetic field above as well. So what will happen to the point here? Again the same thing, this and this, they will again cancel each other. So it is all the points which are on these equatorial line or the perpendicular line, they will all cancel each other. So that means what? Magnetic field here is zero. Same way, magnetic field on the sides of a solenoid in any direction will be equal to zero. So magnetic field here is also zero. So this is an important point to note, that magnetic field outside a solenoid is equals to zero. Right? And we know the reason now why it happens like that. So there is only magnetic field is there only inside the coil. So that's why the topic in the beginning we wrote magnetic field inside a solenoid. So that's what we have to now find or calculate. And we have to apply the Ampere's circuital law for that. So we'll do that as well. Now, before moving forward, one more thing. The Ampere's circuital law, we have seen that in that case, we have to do few things, and they are, what we have to do there is that we should be having a first the point where you have to find the magnetic field. Second, through that point, you have to come up with a Ampere's loop. So that is very important, that you should have a Ampere's loop. You should create an imaginary loop, that is Ampere's loop. So that we are going to do. Okay. Next is, what is that Ampere's loop? Yesterday we have seen that Ampere's loop should be such that most of the, if there is a segment, continuous segment of a you can say loop, then their magnetic field should be constant. Why? Because ultimately we have to do this B dot dl, and if B is constant, I can actually write it as B and dl, integration of dl cos theta. So we try to maintain this. Okay, now that's why for this coil, which we have seen earlier, this coil, if I if I have to consider an Ampere's loop, I will actually see, or I'll actually create a loop like this. So I don't have to find now magnetic field outside. So let us have, say this is our point P. Say this is the point P where we have to find the magnetic field. So what we will do, we will consider a loop like a rectangle, a rectangular loop like this. Now that loop should go through the point P. That is the only thing we have to consider here. Now what happens here is, now consider there are a separate rectangle here because this is a rectangular loop. So now consider a separate rectangular loop here like this. So suppose this point was A, B, C, and D. So this is the magnified view of the same A, B, C, and D. Okay. Now, if I have to find BDL of this DL, small segment on this, can be thought of moving or consisting of 4 parts. So what do we have to find? We have to find B dot DL of this closed loop. So what we see here is that this B dot DL, which we have to find, can be actually modified, you can say divided into 4 segments. That is, for segment A to B, then segment not closed here because this is no more closed now. Right? This plus the same thing for segment B to C, then the same thing for segment C to D, and the same integration for segment B to A. So from where we started A, we ended up at the same point A. Now this is the closed or total integration, which has been divided into these 4 integrations. And inside, what do we have? We have the same thing, that is B dot DL. Here also B dot DL. Here you have the same B dot DL. And here you have the same, that is B dot DL. Now, out of these, we have already proved that in the section A to B, this section A to B is outside the coil. So here B is equals to 0. So that means what? That means this section I can ignore because this is equals to 0. Now consider the section AD and BC, that is this section and this section, AD and BC. In AD, B is perpendicular to DL because we are going either in this direction or in this direction. Both the case, B and DL are perpendicular. Here also B is perpendicular to DL. So in both the cases, what do we have? We have theta is equals to 90 degree. So cos theta is equals to 0. So here also cos theta is 0. So that means even this segment and this segment is gone. They both, all these 3 will actually contribute, their contribution will be 0. And that is the reason for that. So what do we have? We have only this part left. So we have to find or integrate only this part. So let's do that now. We have B, and this we have to use to find magnetic field. So don't forget that. this D to C or C to D is actually the length of solenoid, right? And solenoid has a property called N. This small n is number of turns per unit length, right? And suppose L is the length of the solenoid. So total number of total number of turns will be how much? N into L. So this is the total length, N into L. Okay. Now what do we have? We have this. And what about the angle between DL and suppose if we are moving in this direction, then DL and V are in same direction. We'll move in such a way that DL and V are in same direction. So in that case, what will happen? If DL is in this direction, V is in this direction, so theta is equals to 0 degree and cos theta is equals to 1. So due to that, what happens? B dot DL is equals to VDL. B dot DL is equals to BDL. So now you just have to integrate the DL, and that should be equals to mu naught into I. I is the total current. So current in one coil is I. So current in N coils will be N into L into I, where I is the current in one coil, right? And what is there on the right hand side? You have B into L. That is equals to mu naught into N into L into I. So now what do we see here? This L and L gets cancelled. So the final magnetic field which we have here is or will be given by B is equals to mu naught N I. And there are few points which we have to remember. It depends obviously on the mu, that is, or the permeability or the medium, so leave that. Apart from that, it depends on N. So B is directly proportional to N, where N is not total number of lines. N is actually the density or how dense the turns are there. N is actually number of turns per unit length. So more dense or more closed or closely packed lines will be there in solenoid. It will have more magnetic field in the axial line. And if they are loosely or you say there is a lot of space between these lines, then the magnetic field will be of less strength. And obviously you increase the current, there will be more magnetic field, right? And that in that simulation also we have seen, you can see that if you increase the current, the magnetic field vector will be of greater length, will be of more length, or its length will be more. That means its magnitude is actually more. So this mu naught into Ni, again, very important derivation, which you will find use in the next chapters as well. So try to now understand this, how the derivation part of this, the logic behind this, and we will be using the same derivation again when we'll be studying the toroid. So we'll need this again. So that's why revise this again, try to do this derivation yourself and see if you are able to do it or not. Okay, so that's all for today. In the next class, we'll do derivation for toroid, and once that is done, we'll do some numericals first and then we'll move to the next topic. Any doubt? Anyone has any doubt, you can ask, and I'll send the PDF of this to you so that you